So good afternoon, everyone. I think today is my turn to entertain you for a few hours. Well, one. And today we're going to talk about the Monte Carlo integration and giving you some theory on random numbers. And we'll also have some examples on how to use random numbers in C++. I think today's lecture will be maybe a bit shorter than usual, but hopefully you still get some useful instruments out of this lecture that you can use even in some other examples. So let's first look why we care about Monte Carlo integration. One of the main issues of the Simpson algorithms that you already implemented a few times already. So we know that the Simpson integration, it's a fourth order scheme in one dimension. But when we go to higher dimensions, in this case, keeping the number of beans fixed, the accuracy of our results is going down with the number of dimensions we have. Exactly, the accuracy is m to the power of -4 divided by d. But d is not only 1, 2, and 3 dimensions like we're used to. In usual calculation, when, for example, we deal with classical mechanics, the number of dimensions is already 6 times n, where 6 is because we have 3 dimensions for the positions and 3 coordinates for the velocities as well. Then another example are classical spin problems. In this case, we only have 2 angles per particles, so 2n. But the problem is, for example, when we go to quantum mechanical systems, for example, a quantum spin-S problem has an exponentially increasing number of dimensions that we have to solve. So from this, we see that D can actually be quite huge. What can we do then? So let's start from an easy example. Maybe you have already heard or now you can compute pi by just throwing stones. So the idea here is that we know that the surface of a circle, or a quarter of a circle, in this case, should be given by pi over 4, well, given that the radius is 1. And the method here is that you just create a box around your circle, and you just start throwing stones. And you basically end up filling the whole squares with stones, lots of dots there. Then, if we take the ratio of the number of points that are in the green area compared to the number of points that are that we throw in total, that just this number is exactly the ratio of the 2 areas. Because I think you would agree that the larger the green area is, the more probable is to throw a stone in this green area. And so that's a nice introductory exercise, and I think you will do that next week. So I'm not giving you any further explanation solution, since you're going to have fun with this. Now let's try to apply that to a more realistic problem when, for example, we want to integrate a function. So in the first case, we want to get the average value of a function f, and function f can just have some arbitrary shape. If we do some, for example, a Simpson integration scheme, we have to introduce many bins in the system, and then we can compute the integral just by summing them up. But what we can also do, and that's the Monte Carlo integration, is to just get the value of the function at some random positions. So here I really mean some random positions. So for example, once I measure here, once here, one is moved slightly to the right, and so on. So if we just have 5 points, that's a bad result. But if we start increasing the number of random points we keep, we slowly converge to the right solution. And actually, the only error that we have in the Monte Carlo sampling, it's the statistical error. And we know that from statistics, the the delta on the mean value that we get, it's going to scale asymptotically with the square root of the number of points minus the square root. I mean, 1 over the square root of the number of points. Meaning that the more points we have for this Raman sampling, we will eventually get the exact solution of our integral. And so that's a constant scaling as a function of the dimensions. And if we take the m to the power of minus 4 divided by d that we used to have before for Simpson, we see that already after the dimension, after 8 dimensions, Monte Carlo results will scale better than the Simpson integration. Now, what was describing to you previously, just taking random points, that's what it's called the simple sampling of Monte Carlo. But the problem is that if the variance of the function is big, so let's imagine we have a function that it's almost 0 and it's just going up in a small region just in a small space, it's going up a lot. But otherwise it's almost 0. If we take random points everywhere, it's very likely that we just sum up zeros because we are in the flat part of the function. And to have the correct results of the integral, we have to sample many times in the peak where the function is very high in the value. And to do so, we can do importance sampling. This means importance sampling means that we don't sample point x uniformly, but according to a distribution probability p. So if p it's very similar to the shape of our function f, it means we will sample more and more points where the function has higher values. This means that we don't have to throw away many evaluation of the function, and we just have to, with the same number of points, we get a much better convergence because the error is only determined by the variance of the ratio of the two functions. Now, if f and p are exactly the same, the variance of a constant function is 0. So that's just to give you exactly what we do, and I now can actually just show you in a mathematical example how this importance sampling works. So now I have an example for Monte Carlo integration is this one. Okay. So we want to compute the integral of the function f, which is the exponential of minus x squared, up to from 0 to an endpoint 100. Then, so just do the integration, and so we know that the integration cannot be solved analytically. It's just this error function, but we can evaluate the correct results, and that's something like 0.88. Now, let's do the same integration with Monte Carlo. So we have to load some statistic package. So this example is also online, so you can also run it yourself and you can play around with the parameters. So to compute the integral, we will use 10,000 points. In this line, we create many random numbers according to a uniform real distribution, so means from random numbers from 0 to 1. And then we multiply times the volume that we want to, so the length of the volume we want to have random numbers in, so that we, instead of getting numbers from 0 to 1, we get them from 0 to the end of our range of integration. And then we can just evaluate the mean. And in this case, you see that the mean should be the actual integral that we solve. And with 10,000 points, we get a value of 0.91, which is, well, just comparing to the previous to the exact solution that we computed before, we have a relative error of about 3%. So still not bad, but could be better. And to be better, we just do importance sampling. So we have to choose a distribution probability P, which is close to the one we want to integrate, to the function f we want to integrate. So in this case, we take P to be an exponential distribution. So that's just the exponential of minus x. This part is to normalize our probability distribution, so that the integral over the integral from 0 to n, it's going to be 1. What we have to do is to sample the function g, which is the ratio of the two. You remember, it was on the slide. And next line, 22 here, it's something we will actually discuss in some slides later. That's doing the transformation from a uniform random number distribution to an exponentially decaying random number distribution. To do so, you just have to apply this formula. Why it works, we will just show later. So then we get to the point where we sample the function g at all these random points that are distributed exponentially. And this time the mean is 0.88. You remember before the exact solution is 0.88. And we went from a 3% of error to 0.7%. So I think this was everything I had to tell you on Monte Carlo integration. It's very easy. Just sample the function you want to integrate at many random points, and the mean is going to be the average value of the function. I think you will practice more in the next exercises. So what we have learned from Monte Carlo, well, we have learned that we need random numbers. How do we create random numbers on the computer? So we could try to get real random numbers, but these are really hard to obtain. You can rely on some physical system where, for example, cosmic radiation, atmospheric noise, could be really some random effect, and you can just take, I don't know, measure the atmospheric noise, and you get all the peaks that are your random numbers. You can also use some quantum mechanics to get quantum numbers. That's, for example, this little box there that you can buy from a company in Geneva who's actually selling these devices, for example, to online casinos and other companies. And they're actually making lots of money because they are a proven quantum random number generator, which is proven by a Swiss authority to be certified to be random. Well, we don't have such a device. We cannot really measure atmospheric noise and cosmic radiation. We just want to generate a random sequence with our computer. And to do so, we'll just rely on pseudo-random numbers. Pseudo-quantum random numbers are just numbers that you compute with an algorithm. So they're not random at all, because you know exactly, given all the numbers, you know exactly what's the next number that you're going to sample. But they're not random, completely deterministic, but maybe the sequence is random enough for our purposes. But an important message is never trust a pseudo-random number generator if you really want random results. So a few examples. The basic random number generator that you might already have used, for example, in the PENA model, it's the linear congruential generator. In this case, we have one random number xn, and we apply a linear transformation to get the next one. So for example, for a linear transformation, in this case, we multiply the previous number times a constant a, we add another constant c, and then we just take the modulo with m. Here you get some nice numbers. So that's also the one you implemented in the exercises. So you should be familiar with the equation. be aware that this random number generator, only a few special cases of the variable a, c, and m will actually give you a full sequence that has the length of m. If you take just some arbitrary values for a and c, you might really have a very short sequence, which is really a bad quality random number. And another note is that even if you manage to have 2 to the power of 32 random numbers, for an actual simulation, it's not really a lot. And at some point, you will start repeating your sequence. So a better solution is, instead of having just one number as the previous, just one number for the state, which is your previous random number, you have the whole history of random numbers that you created before, and you don't create a new number working on the previous one, but on 2 of the previous one. And actually, the previous one minus p and the previous one minus q. And with them, you do some binary operation. Could be whatever arithmetic binary operation, the sum, multiplication, or, for example, a logical XOR. It's also good. A good example here of choices to have. So this column is P, this is Q, and this is for the plus operation. So if you just want to implement at some point your own left Fibonacci random number generator, that's some reference values you can use. As I said, you need the full history of random numbers, but if you're just starting your random number generator, you need to generate a state of previous numbers. And to do so, you usually initialize your generator with a linear congruential that we've seen before. It's also a very good random number generator because you can implement it efficiently. And on vector machine, you can use vectorization. You can have nice pipelinings and compute many. In the end, you can compute many numbers in parallel if you want a sequence of random numbers. But the main question that we're still asking is, are these random numbers really random? Well, it's an algorithm, so it's not random. Maybe it's random enough. And to see if it's random enough or not, we can run a few tests. So there are standard test suite that do some tests on the distribution. If you have correlation between numbers, like if I get now number 2, what is the probability that I get again a 2 if I start sampling 10,000 random numbers? But in the end, that's really just some specific test. But none of these standard tests, it's in the end going to really check what is the a possible problem in your simulation. There might always be some hidden correlation that it's not covered by the test before, and only your simulation is the test for this random number. So an important take-home message, when you use random number generators, it's always a good idea to try different generators, different seeds, to see if the results is really influenced by the choice of the random number generator. If your result is always the same, then, well, you could say it's a converged result. It doesn't depend on the choice there. Now, just look at some. We can now look at some example how to test a random number. The easiest way to test, well, let's just plot the numbers. So we have an example, another Mathematica notebook, where we use a self-made linear congruential generator. So that's again the formula you've seen before. We create a sequence of m random numbers, and then we take a pair of them. We take the number, so we take one number and the next one, and this will be our x and y coordinate that we plot. Or we take 3 of them, and this is going to be x, y, and z, and we just plot them. So now let's just look at the results. So if we plot a pair of numbers, so do you think that's a random result? Or can you see some correlation? Well, if you cannot see correlation in 2D, maybe you can see them in 3D. So that's just to show you that's a very, very bad random number. Even on the surface of a sphere, you can actually create some nice patterns. But so let's look at the good random numbers, which is the one built inside Mathematica. Now I think I have to run it. So we do the same stuff. Again, M random numbers. We create a pair, triplets to do the 3D plots, and to plot on the surface, we normalize them to be with radius 1. So let's plot now the 2D, and well, that's how it should like. That's really a random uniform distribution. We don't have almost any correlation pattern. 3D, much better. And on the sphere, it's also quite random. Okay, so that's testing. Now we have uniform distributions. All the random numbers we were talking about are giving you numbers. It's a uniform distribution from 0 to 1. Now let's try to do some improved distribution. We want to, for example, to have random numbers between 10 and 20. In this case, the transformation is very trivial. Just multiply times the distance between the two in the range, and you do a shift. But what if we want a non-uniform distribution? If we want to sample according to an exponential distribution or a normal distribution? So to do so, we have two methods, and we are quickly going through them now. So first of all, a bit of definitions of probability. So a probability density function, p of x times dx, is giving you the probability of finding a number of hitting a number x plus minus a delta x around this number. And the smaller you make your delta x, this probability is going just to vanish. What we can look at, it's a finite probability of finding a number between a range. For example, a range between a and b, we just integrate all the infinitesimal probability, and we get a finite number out of it. So an example of probability distribution for the uniform probability distribution, that's just 1 between 0 and 1 and 0 otherwise. The other useful quantity we usually define is the integrated probability function, a capital P of x, which is the probability of having of throwing a number smaller than x. So it's just the integral from minus infinity to our upper bound x. Now we want to change the distribution. So what we want to achieve is to sample a random number x according to a distribution f of x that might have this wiggly, strange density profile. To do so, we have to think about the integrated probability. So what we can do is to say, what's the probability of throwing a random number and getting a number which is smaller than this capital X. So to do so, we integrate our probability distribution from our lower bound to capital X. And now we want to represent the same probability, but by using a uniform random number. So a uniform random number is just the shape here, and we can simply integrate a constant, and this is just the limit of the integration, capital U. On the other side, we have this integrated probability density, integrated probability, capital F, and in the end we want to transform u into x, and the transformation is just the inverse of the integrated function f. So that's the recipe, but you have two important ingredients that you have to be able to fulfill. First of all, you have to be able to integrate. Second, you should be able to invert the function. A few examples in case where we can do integration and we can invert. As I mentioned before, in the example of the Monte Carlo integration, we have a probability density, an exponential distribution. So it's defined by lambda times the exponential of minus lambda x. And now we apply our formula above, we integrate, we invert the equation, and we see that the numbers, we have to transform the uniform random numbers u according to this formula to get the x, which is distributed with this probability density. Similar we can do for random numbers in a circle, if we want to get them uniformly distributed inside the circle. Again, here it's some reference transformation in case you need it. And let's go now to the normally distributed random numbers. So, as I said, we have to be able to integrate and to take the inverse. So in the case of the normal distributed numbers, unfortunately, we cannot solve analytically the integral above. But there are some tricks. We can still compute the square of the integral. And that's what it's used in the Box-Muller method. And what you end up, it's a transformation from two uniform random numbers. You can compute two normally distributed random numbers. Now, in case the integral is really hard, you cannot solve it, you cannot use any trick, you still want to be able to have numbers distributed according to your distribution, density distribution, f of x. The second method we can use is the acceptance rejection method. And in this case, for example, we have the orange distribution. And what we can do is define an upper bound of f of x. That's lambda times h. And the assumption is that we can throw numbers according to h. If we can do so, then the algorithm looks as follows. We throw a number x according to the h distribution. Now, since the density h has a maximum in the middle, it's much more likely to get a point in the middle as well. Then, next, we sample a uniform random number on this line, which is going from 0 to the current value of lambda times h of x. So let's do so. And then we check the condition here, which simply means, which I can just take this part on the other side, it's just telling you if our point is below the orange line. So in this case, it's okay, and we accept the point. We can repeat, we sample a point there, another uniform random number, and we go up there. In this case, the condition is not satisfied, so we just reject the point. Repeating many, many times, we end up filling up the full surface, and all the points here, I mean, once you finish, all the points you have a next component which is distributed accordingly to our function f. Now, I've shown you before in the example when we have a number here, it was very likely to end up in this region up there where we are above the orange line. This means that to be able to have an efficient acceptance rejection method, we have to choose a distribution h, which is very, very close to f. The closest we are to f, the less points we have to reject. Oh, so this was everything on the theory of random numbers. Next, we will move to the how to use them in C++. So do you have any questions for the moment? Everything clear? Good. So how do we use random numbers in C++? So we are very lucky. Oh, now I have to run it again. We're very lucky. In 2011, a new standard of C++ was released. You might already have heard about C++11. And in C++11, we have a standard library for random numbers. Now, the new standard, it's quite new. It's not completely stable in all compilers, but now we are at the stage where it works and we can start using it. So just to warn you, the standard library printouts that you got last week are still for the old standard library, the one of 2003. I think in this lecture overall we will cover the old standard, and it's only for some tiny details that we go to the new standard. Maybe in the next year we will move completely to the new one, but now it's still sort of unstable to really use it in production. So how to use C++11? For most compiler, it works. Everything you have to do is to add this option to your compilation, -std equals C++11. In case you have the Clang compiler and you want to use the random number library, you also have to add this option to use the libc++ standard library. If you don't have the Clang compiler or a recent version of the GCC, you can always rely on the Boost random library, which is there, works with really many compilers. And actually the Boost random library, it's just an header-only library. And you can just download the sources from the Boost website. And when you compile your program, you just have to put an include flag for the include of Boost. And you don't have to do any kind of strange installation. So I'm going to show you examples on how you do on how you use random numbers in the standard library. Some example for Boost, but if there is no example, most of the time you can just exchange the namespace from std to Boost, and this usually works. So a generator, a random number generator, it's usually as usually it is interface, so it's actually interface required from the standards. You have a result type, which is the type that you get from the random number. Most of the time it's an integer, or could be a double, for example. Well, for sure you can construct it. If you call the default constructor, you get a default initialization. So you get a default state for your random number generator. You can give some parameter that we'll have a look later to give your own initial state. The same can be achieved with a seed function. And when you use it, it's like the interface you implemented in the previous exercises. You just have the operator, the access operator, the operator parentheses like that, which is giving you the next random number in the range min and max. A few examples of random number generators. They are in the random header of the standard library. A good choice is usually the Mars and Twister random number generator. You have a few variations of them. I'm just listing a few. If you really want all the details, what they do, you can just go on a reference documentation and you see a really huge list of generators that you can use. So as I said, we have Mars and Twister that are an improved lect Fibonacci generator. We have the lect Fibonacci using a subtract with carry binary operation. And we also have the linear congruential that, well, we know they are not really good, but you can still use them. In Boost, the names are slightly different, and they include, it's this time boost/random.hpp. But again, you still have a few Mars and twistor generators, like Fibonacci, and I think the linear congruential actually have exactly the same names. How you seed the random number? There are usually two ways. Once you construct your random number generator, MT, with a seed function, you can either provide a number, just the seed of your random number generator, and this will, and internally, for example, the Martian twistor is similar to the leg Fibonacci as a vector, as a huge vector, as a state. It's using your seed to build this huge state. That's one way. The other way, since you have to build this huge initial sequence, there is a better way to not just provide one number to the generator, but to provide a list of numbers. Like in this case, we provide n different seeds, which might give some more randomness to our problem, and we can use the seed sequence class of the standard library, where we copy over the seeds that we created, and we can seed the random number generator with the seed sequence. Distributions, so was a huge story on how to tell you how you do the distributions, but in the end you don't have to do much. They are already implemented, you just have to use them. Distributions are again in the namespace seed, and usually you build them given the parameters that you want for your distribution. For example, integer distribution between 10 and 20, you just give it a parameter. A real distribution, you get, for example, between 0 and 1, you get all real numbers between that. Just be aware there is a small difference between the integer and the real distribution. The integer is going to give you numbers between A and B included. The real distribution, B is not included. Then exponential distribution, the one we used before, and for the normal distribution, you again just give the standard deviation and the mean and the standard deviation. So everything together in a nice example. We have the random number engine. We create a list of sequence. In this case, we just create what? We create 16 seeds by using a linear congruential generator. Then we initialize the distribution. And to use the distribution, you just call your object by passing the random number engine that you want to use. So for this, we can try to run it. But instead of running this simple code, which is, well, it's doing nothing, it's a bit boring, we can look at the second example. In this case, we do the same. We initialize, we create the sequence, but instead of just pointing out one number, we create, with the function point distribution, we create an histogram of the random number. So we can actually plot the distribution that we are sampling from. So what's important here is that you have to pass, just be careful, every time you pass the random number engine in a function, check that you pass it by a reference. If you pass the random number engine by value, it's going to be copied and it's not going to update its state. So every time you call it, you just get the same numbers. So that's the code. So do you understand it, or I have to explain some lines? Fine. So now let's just have fun and run it. As I said, we compile it with the compiler, C++. We have to give the option for C++ 11 and the source. Okay. Here we go. So as you see, the program is just printing out this integer distribution. It's constant. It's a uniform distribution with some random noise. Good. It's random. The real distribution, this time is more flat. The exponential distribution actually looks like an exponential, nice. And eventually the normal distribution that we decided to pick around a mean of 2, if I remember correctly. Or yes, no, mean was 3 and the standard deviation 2. But still the 3 is a maximum. Okay. Now a small, let me just go back here very quickly. So it's actually so that people actually find quite annoying that when you have to call the random number a distribution, you always have to pass the random number there. So this means that you cannot pass the distribution like it is now to, for example, a generate function. You have seen in the standard library there is the generate function which can fill in a vector or a list with calling the same function many times. But the requirement on this predicate function is that you can just call it without any argument. So you can either define your own function object, or maybe you will see later in the class that in C++11 you can now use what it's called the lambda function. But in the Boost library, this was solved in another way. The Boost random library provides you this variate generator object, which is doing nothing else than just taking. So it takes an engine and a distribution, and in the end you get out an object, RNG, that you can just call without any argument. So this is very convenient if you have to pass it to some standard library or some other generic function that has this requirement. So we are almost done. Just have a few advice for you, especially when you have to use random numbers, and for an example, it's already in the Penna model. So what you have to be really careful when you use pseudo-random numbers, you have to seed your random number only once. Otherwise, I mean, it's full of wonderful theorem showing you that a random number generator is good. But this is only valid if you keep it in the same state. I mean, if you just go on from a state. If you change the state of your random number all the time by seeding it more often, then you completely destroy every theorem that could prove you that this is a good pseudo-random number generator. So how to usually seed it? Well, it could be a fixed constant. That's also fine. Usually we have an input parameter. Our simulation just reads in the seed, and they're going to use it in the code. It's also very good practice to print out your seed. So that if you run your simulation, you know exactly what was the initial seed. And in case there is a bug, you can reproduce exactly the same sequence, and you can reproduce the bug. Because if you do, I don't know, Monte Carlo integration, maybe the bug is there only sometimes, it's random. If you change the seed all the time, you have no way to reproduce exactly the same sequence, so you cannot reproduce the problem. So print out the seed so you have a reference to reproduce the results. And never trust the generator before trying several of them. I skipped one point, which is also, so you can also seed with the current time, but it's not really advised. You could. It's not a problem, but only do that once and point out the seed afterwards. Now, just to finish, just want you to show what happens if you seed your random number generator more than once. So I just copied over from a solution I got from the Penna model, the genome class. So I think now you know that pretty well. But what's not really good in this code is that someone is calling the seeding inside the mutate function. and always seeding with the current time. So as I said, that's really bad. You should never seed the random number generator twice, and especially not twice with a time. Then we do some tests. So in the main, we create a genome, we print it out, we mutate, we print it out again, and we mutate again, and we print out. So let me just show you why it's bad. So, well, okay, there is line wrapping. So in the beginning, we have an empty genome. Then we actually introduce some nice random mutation. And then afterwards, we print out again an empty genome. So do you know what happened here? So the time function we use to seed the random number generator as a lower resolution that actually the time it took to call twice the function mutate. So we created exactly the same random sequence. So all the mutation we just introduced, they just vanished. And we basically always use the same random numbers. Okay, I think it's already the end of the lecture. As I told you, it was shorter than usual. Any questions?